Okay, now let's talk about risk. To really understand the concept of risk, we have to first understand incidence and prevalence. Both incidence and prevalence are measures of occurrence, and both in some way incorporate time into their reporting. Prevalence is a measure of the proportion of the total population affected by a disease or outcome, either over a specific time period, as in period prevalence, or at a specific point in time, point prevalence. For point prevalence, the total number of cases at a specific point in time are divided by the total population at that time. For period prevalence, the number of pre-existing cases is added to the number of new cases that develop over a specific period of time, and their sum is then divided by the average of the population during that time period. Incidence reflects the proportion of an unaffected population that becomes affected in a period of time. Depending on how the study is constructed, incidence can be expressed as cumulative incidence or as incidence rate. Cumulative incidence, also called incidence proportion or attack rate, is equal to the amount of new cases that develop in a specific fixed period of time divided by the population at risk during that period of time. This fixed period of time is not numerically reflected in the denominator. For example, in the United States, the cumulative incidence of tuberculosis in 2020 was 2.2 cases per 100,000 persons. On the other hand, incidence rate is the amount of new cases divided by the amount of person time, or the sum of time, typically in months or years, that each subject was followed and at risk. Incidence rate has the advantage of incorporating data on persons who were followed for only a portion of the study. So if a patient leaves the study early, their data up to their point of departure can still be incorporated. Incidence rates are typically reported in units like cases per person years. However, these units can also be converted to cases per persons per year. For example, one study reported that the incidence rate of heart failure in Dutch 55 to 64-year-olds is 14.4 per 1,000 person years, or 14.4 per 1,000 persons per year. The population in this study was followed for over several years as people entered and left the study for various reasons. However, the study results were still reported in terms of person years. In the context of epidemiology, the terms risk and cumulative incidence are interchangeable and defined as the amount of outcomes or cases of disease that develop over a specific time period divided by the total number of at-risk persons in that time period. So, when we conduct a cohort study or a clinical trial, we are measuring the number of outcomes per number of people in each group over the course of the study period. Thus, we are recording the cumulative incidence in the two groups, the exposed and the non-exposed, or the treated and untreated. We refer to this cumulative incidence as the risk, or absolute risk, the word absolute being used to differentiate risk from a proportion like relative risk. So from here on out, I want you to equate risk with cumulative incidence and vice versa. Comparing risk in a control group to risk in a group under study is the most fundamental method of comparison in a cohort study or a clinical trial. From absolute risk, we calculate the risk ratio, or relative risk, which is the proportion of risk in exposed relative to unexposed, or in treated relative to untreated. And proportion is another buzzword that we have to keep in mind. From here on out, I want you to associate words like relative and percent with proportion, and proportion with terms like times as likely, percent increase or decrease, or percent more likely. For example, let's assume that the relative risk of developing outcome Y that is associated with exposure A was 1.2. We can interpret this as a patient exposed to exposure A will be 1.2 times as likely to develop outcome Y as a non-exposed person. Another interpretation can be made using percentages. For example, assuming a relative risk of 1.2 again, we can say that persons exposed to exposure A are 20% more likely to develop outcome Y than those not exposed. Now let's say that the relative risk of developing outcome Y that is associated with exposure B is 0.4. We can say that patients exposed to exposure B are 0.4 times as likely to develop outcome Y as those not exposed to B. We can also say persons exposed to exposure B are 60% less likely to develop outcome Y than those not exposed to B. It's important to note that although in our everyday conversations, the words likelihood and probability are taken to mean the same thing, in the context of statistics, there is a distinct difference. The probability of an event communicates how likely it is for the event to occur, while the likelihood describes joint probability, meaning the probability that one thing is true given another thing is true. As implied by the examples, a relative risk greater than 1 indicates a positive association between exposure and outcome, less than 1 a negative association, and equal to 1 indicates no association. Another cool thing about relative risk is that it can be used to communicate both risk increase and risk reduction. However, other measures of risk can be used to illustrate risk increase or risk reduction based on whether a study is investigating a potential risk factor or a treatment. There are quite a few of them, and you may feel the compulsion to cry or roll up into the fetal position under your desk, but hold on and push through because these measures of risk increase and risk reduction mirror one another very closely, and hopefully the examples we'll go over at the end will tie them all together. So let's start with the risk increase. When we are dealing with a potential risk factor, we expect that the risk in the exposed group will be greater than the risk in the non-exposed group. As stated earlier, relative risk in regards to a risk factor communicates the proportion of risk in the exposed relative to the unexposed. Relative risk increase, on the other hand, communicates the proportion of risk increase in exposed relative to unexposed, with the keywords here being proportion and increase. But what does this even mean? To better understand it, let's take a look at attributable risk. Now, attributable risk reflects how much of the total risk in exposed persons can be attributed to their exposure. And contrary to relative risk increase, attributable risk represents the absolute risk increase associated with exposure, or by how much an unexposed person's risk would increase if they were to become exposed. From attributable risk, we can derive the number needed to harm and the attributable risk percent. Attributable risk percent estimates the proportion of disease in exposed patients that is attributable to their exposure status. It differs from relative risk increase in that the denominator for attributable risk percent is the risk in exposed. Simply stated, relative risk increase communicates how much worse it could get, while attributable risk and attributable risk percent communicates how much of the badness is due to exposure. Number needed to harm is a value that communicates how many patient exposures need to happen for one unfavorable outcome to occur. And when you think about it, it makes sense that the number needed to harm is the inverse of attributable risk, since they both represent risk in an absolute sense. Alright, example time. Let's suppose the risk of developing a cold over the course of 1 year is 0.4 in non-exposed persons, and 0.7 in persons exposed to cigarette smoking. The relative risk here is 1.75, meaning those who smoke are 1.75 times as likely to develop a cold as those who do not. The relative risk increase here is 0.75, meaning those who smoke are 0.75 times more likely, or 75% more likely to develop a cold than those who do not. Attributable risk is equal to 0.3, meaning that for every 7 cases that occur for every 10 exposures, 3 of them are attributable to smoking. Attributable risk percent is approximately 43%. This means that 43% of the risk of developing a cold in patients who smoke is attributable to their smoking. The number needed to harm is 3.3, which we round up to 4 because it's very hard to find 3/10 of a person. This means that for every 4 persons exposed to smoking cigarettes, a new case of the cold will occur. The counterpart of risk increase is risk reduction. We use measures of risk reduction when we expect that the exposed persons will have less risk than non-exposed persons. In this context, we can say that exposed persons are treated in that they were exposed to the treatment. Relative risk in regards to treatment or a protective factor communicates the proportion of risk in treated relative to untreated, and so is expected to be less than 1. Relative risk reduction communicates the proportion of risk decrease in treated relative to untreated and represents the potential for improvement. Absolute risk reduction is the reduction in risk attributable to treatment. It can also be thought of as the amount of disease that would be eliminated if all patients were exposed or were receiving the treatment. From absolute risk reduction, we can calculate number needed to treat and the preventable fraction among untreated or among unexposed. We calculate number needed to treat by finding the inverse of absolute risk reduction. And again, this makes sense because unit-wise, absolute risk reduction tells us how much risk we reduce per person, while number needed to treat tells us how much people we need to avoid the risk. The preventable fraction among the unexposed is equal to the proportion of cases in the untreated group that could have been prevented with treatment. Now at this point, you may have noticed that the equation looks pretty darn similar to the one for relative risk reduction, and that's because they're the same equation. Relative risk reduction is numerically equal to the preventable fraction among the unexposed. But they are not the same thing. Relative risk reduction is the proportion of risk decrease attributable to treatment, while preventable fraction among unexposed represents the proportion of cases or events in the untreated or non-exposed group that could have been prevented with treatment. The difference is purely semantic, since we define risk and cumulative incidence in the same way. Now let's do another example. Suppose that for persons receiving drug A, the risk of sunburn was 0.3, while those not taking drug A had a risk of 0.55. The relative risk in this case is 0.54, meaning persons taking drug A are 0.54 times as likely as those not taking it to develop a sunburn. The relative risk reduction is 0.45, implying that persons taking drug A are 45% less likely to develop sunburn than those who do not take drug A. Preventable fraction among unexposed also equals 0.45, implying that 45% of cases among those who did not take the drug A could have been prevented if they took drug A. The absolute risk reduction is 0.25, implying the 0.25 decrease in risk of sunburn is attributable to drug A. Taking the inverse of the absolute risk reduction, we get the number needed to treat, which is 4, indicating that for every 4 persons treated with drug A, 1 sunburn will be prevented. One last measure of risk that we will be discussing before moving on is the population attributable risk. Population attributable risk is equal to the risk or incidence of an event and the total population that is attributable to exposure, while population attributable risk percent is the proportion of risk and the total population attributable to exposure. Both are calculating using total risk in a population. And so for our smoking example, let's say that the total risk for the population was 0.5. The population attributable risk would be 0.1, implying that the risk of a cold in the entire population attributable to smoking is 0.1, or that of the 5 cases that develop from approximately every 10 exposures in this population, 1 of them is attributable to smoking. Population attributable risk percent here is equal to 0.2, implying that 20% of the colds in this population are attributable to smoking. Alright, now let's move on from conceptualizing and take a look at a real-world example. In the late 90s, the Titanic was breaking our hearts and tearing up the box office. Destiny's Child was making us say their name and say their name again, and denim on denim was still legal to wear in public. Oh, and a group of investigators were conducting a double-blind randomized control trial to measure the effects of lovastatin on the incidence of major cardiac events. They did this by randomly assigning 6,600 patients into a lovastatin group and a placebo group, and then measuring the incidence of different outcomes between the two groups, with the main outcome being acute major coronary event, which they defined as acute coronary syndrome or accelerated rest angina with ST elevations. Now before we start, I just want to point out that although we have a control group, the placebos, and a group under study, the lovastatin, this is not a cohort study. Since an intervention is introduced by investigators, this is classified as an experimental analytic study, which in this case is a clinical trial. Alright, so question 1. What is the relative risk of unstable angina in patients taking lovastatin compared to patients taking placebo? The first step to finding relative risk is to find the risk in each group, which we get by dividing the number of cases by the number of at-risk persons for the control and treatment groups, and then dividing the risk in treatment by risk and control group. Although you don't need a contingency table for this problem, here's one just in case it helps. Keep in mind that because we're calculating risk, we don't need to know the number of unaffected persons in each group, only the number affected and the total. After doing some math, we come up with 0.69, which we can interpret as persons taking lovastatin are 0.69 times as likely to develop unstable angina as those taking placebo. Question 2. How many patients need to be treated with lovastatin to prevent 1 acute major coronary event? So this question is essentially asking for number needed to treat. In order to calculate number needed to treat, we first need to calculate the absolute risk reduction, which is the risk in the placebo group minus the risk in the lovastatin group. For this question, we are interested in the risk of acute major coronary event. We calculate an absolute risk reduction of 0.0224. And then we calculate the inverse, which is 44.64, or 45, which means that for every 45 patients treated with lovastatin, 1 acute major coronary event will be prevented. Question 3. What is the relative risk reduction of revascularization procedures in patients taking lovastatin compared to patients taking placebo. Now we could plug in a bunch of numbers, calculate the relative risk reduction, or we can use our algebra noodle to make this here equation all nice and simple like. By doing that, we come up with 0.33, which can be interpreted as a 33% reduction in the risk of undergoing revascularization. Lastly, question 4. Based on the table above, which of the following is an accurate statement? Answer choice A. Compared to a placebo, patients taking lovastatin are 0.7 times less likely to suffer a fatal cardiac event. This question makes an incorrect interpretation of relative risk. It would be correct if it stated that patients taking lovastatin were 0.7 times as likely to suffer fatal cardiac events as those taking placebo. B. Compared to a placebo, lovastatin was associated with a 37% decrease in rates of acute major coronary events. This one seems legit and actually is the correct answer. It correctly uses relative risk reduction to convey results, which are statistically significant. Answer choice C. There was no statistically significant difference in rates of revascularization between placebo and lovastatin. The corresponding p-value and confidence interval for relative risk of revascularization and statin group indicate statistical significance. Answer choice D. Patients in the lovastatin group experienced a 68% decrease in risk of unstable angina compared to the placebo group. This question makes an incorrect interpretation of relative risk reduction, which in this case would be 0.32. Also, this piece of data is a great example of how confidence intervals can be more useful than p-values. The p-value for unstable angina indicates a 2% chance that the result was obtained due to randomness, and thus communicates that it is statistically significant. However, the confidence interval ranges from 0.49 to 0.95, which seems to suggest that a 50% reduction in risk and almost no effect on risk are both consistent with the data, which indicates an inadequately powered study.